Welcome to this comprehensive scientific lecture on how to test and analyze the properties of food and culinary dishes to improve them. Today we'll explore rigorous scientific methods used in food science laboratories and professional kitchens. Before we dive into specific tests, let's ask ourselves, why do we need to scientifically test food properties? The answer lies in quality control, recipe optimization, nutritional enhancement, and consumer satisfaction. Food testing falls into four main categories: physical properties, chemical properties, microbiological properties, and sensory properties. Each category requires different techniques and equipment. Let's start with physical property testing. These are properties you can measure without changing the chemical composition of the food. One of the most important physical tests is texture analysis. We use an instrument called a texture analyzer. This device applies controlled force to food samples and measures resistance. Here's a simplified diagram of a texture analyzer. The probe descends at a controlled speed and penetrates or compresses the food sample. The instrument records force versus distance data. The texture analyzer measures several key parameters. Hardness is the peak force during first compression. Springiness measures how well a product returns to its original shape. Cohesiveness indicates internal strength. Hardness is simply the maximum force measured in newtons. Springiness is the ratio of the distance during the second compression to the distance during the first compression. Let's consider testing bread texture. Fresh bread should have low hardness, indicating softness. As bread becomes stale, hardness increases dramatically due to starch retrogradation. Now let's discuss viscosity and rheology testing. This is crucial for liquids, semi-solids, and emulsions like sauces, soups, and batters. Here's an important question. What is a viscometer and how does it work? A viscometer measures the resistance of a fluid to flow. There are several types, but rotational viscometers are most common in food labs. In a rotational viscometer, a spindle rotates at a controlled speed within the sample. The torque required to maintain that rotation is proportional to the fluid's viscosity. Viscosity eta equals shear stress tau divided by shear rate gamma dot. This fundamental relationship defines Newtonian fluids. Foods can be Newtonian or non-Newtonian. Newtonian fluids like water and oil have constant viscosity regardless of shear rate. Non-Newtonian fluids like ketchup and yogurt change viscosity with shear rate. Consider optimizing a tomato sauce. If viscosity is too low at 50 centipoise, the sauce is watery. Target range might be 200 to 400 centipoise for proper coating ability. Color is a critical quality attribute. Professional food scientists use colorimeters to quantify color objectively, removing human subjectivity. The most common system is the CIE Lab color space. It uses three coordinates: L star for lightness, A star for green to red, and B star for blue to yellow. L star ranges from 0 for black to 100 for white. A star is negative for green and positive for red. B star is negative for blue and positive for yellow. The total color difference delta E is calculated as the square root of the sum of square differences in L star, A star, and B star. When baking cookies, you can track browning by measuring L star values. Fresh dough might have L star of 70. Perfectly baked cookies might reach L star of 40. Overbaked cookies drop below 30. Now let's move to chemical property testing. These tests determine the chemical composition and reactions occurring in food. pH measurement is fundamental in food science. It affects flavor, microbial growth, texture, and shelf life. A pH meter measures hydrogen ion concentration. pH equals negative logarithm of hydrogen ion concentration. A pH probe contains a glass electrode that generates voltage proportional to pH. You calibrate with standard buffers before testing samples. Let me give you some pH ranges. Lemon juice is around 2.2. Tomatoes range from 4 to 4.5. Milk is about 6.5. Egg whites are around 9. Here's a critical question. Why does pH matter in cooking? The answer has multiple parts. pH affects enzyme activity, protein denaturation, pectin gelation, and microbial safety. In jam making, pectin requires pH between 2.8 and 3.5 to gel properly. Too high and you get syrup. Testing and adjusting with citric acid ensures proper set. Moisture content dramatically affects texture, shelf life, and microbial safety. There are several methods to measure it. The simplest method is oven drying. Weigh the sample, dry it at 100 to 105 degrees Celsius until constant weight, then reweigh. Moisture percentage equals initial weight minus final weight divided by initial weight times 100. Cookies with 5% moisture are crispy. 8 to 10% gives chewy texture. Above 12%, cookies become soft and cake-like. Testing guides recipe adjustments. Titratable acidity measures total acid content, which differs from pH. This is crucial for fermented products and fruit-based items. In titration, you add sodium hydroxide solution to a known volume of sample until reaching pH 8.1 or 8.3. The volume of base used indicates total acidity. Acidity equals volume of sodium hydroxide times normality times equivalent weight divided by sample volume times 100. Fresh yogurt should have 0.9 to 1.2% lactic acid. Lower values indicate underfermentation. Higher values suggest overfermentation or contamination. A refractometer measures dissolved solids, primarily sugars, by analyzing how light bends through a sample. Light passes through the sample on a prism. The refraction angle depends on sugar concentration. Read as degrees Brix on the scale. Brix measures grams of sucrose per 100 grams of solution. Soft drinks are around 10 to 12 Brix. Jams are 65 Brix or higher. Fresh orange juice is around 11 Brix. You can track fruit ripening by measuring Brix. Green bananas might be 5 Brix. Ripe bananas reach 20 to 25 Brix as starches convert to sugars. Microbiological testing ensures food safety and predicts shelf life. This is perhaps the most critical category for consumer health. Total plate count measures viable bacteria in a sample. You dilute the sample, plate it on nutrient agar, incubate at 37 degrees Celsius, then count colonies. Colony-forming units per gram equals colonies counted times dilution factor divided by sample volume. This raises an important question. What are acceptable microbial limits? For ready-to-eat foods, total plate count should be below 100,000 CFU per gram. For raw ingredients, limits are higher. Specific pathogens must be tested. Salmonella, Listeria monocytogenes, E. coli O157, H7. These must be absent in 25-gram samples for most ready-to-eat foods. To determine shelf life, store samples at different temperatures and test microbial growth over time. When counts exceed limits, you've reached end of shelf life. Water activity predicts microbial growth potential better than moisture content. It measures available water for reactions and microbial growth. Water activity A sub W equals vapor pressure of the sample divided by vapor pressure of pure water. Most bacteria need water activity above 0.9. Molds can grow at 0.8. Below 0.6, almost no microbial growth occurs. Bread has water activity around 0.95, supporting mold growth. Adding humectants like glycerol reduces water activity to 0.85, significantly extending shelf life. Sensory evaluation uses trained human panels to assess appearance, aroma, taste, texture, and overall acceptability. This is where science meets perception. There are 3 main types. Discrimination tests detect differences between samples. Descriptive tests characterize intensity of attributes. Effective tests measure consumer preference. In a triangle test, panelists receive 3 samples, 2 identical and 1 different. They must identify the odd sample. This detects if process changes affect product. Probability of correct identification by chance alone is 1/3. Statistical analysis determines if results are significant. The hedonic scale measures liking from 1, dislike extremely, to 9, like extremely. 5 is neither like nor dislike. This quantifies consumer acceptance. This is a crucial question. How many panelists do we need? For discrimination tests, minimum 30. For descriptive analysis, 8 to 12 trained panelists. For consumer tests, at least 100. When developing a new sauce, conduct descriptive analysis to profile flavor attributes, sweetness, saltiness, umami, acidity. Then consumer tests determine if the profile is appealing. Real food science requires integrating multiple test types. Let's examine a comprehensive case study. A bakery wants to improve their chocolate chip cookies. They'll use physical, chemical, and sensory tests to optimize the recipe. First, measure current cookie properties. Texture analysis shows hardness of 1,000 grams force. Diameter is 75 millimeters. Moisture content is 8%. Measure sugar content, 25% sucrose. Fat content, 20% from butter. pH is 7.2. Water activity is 0.7. Trained panel describes current cookies. Moderately sweet at intensity 6, slightly crispy at 5, butterscotch notes at intensity 4. Consumer feedback indicates cookies are too hard. Target: reduce hardness to 600 grams force while maintaining crispness. Enhance butterscotch flavor. Increase butter by 5% to reduce hardness. Add 1% brown sugar to boost butterscotch notes. Reduce baking time by 2 minutes to lower moisture loss. New cookies test at 550 grams force hardness. Moisture increases to 9.5%. Butterscotch intensity rises to 6.5. Consumer testing shows hedonic scores improve from 6.2 to 7.8. Success, but now verify shelf life hasn't decreased due to higher moisture. Store cookies at room temperature and 25 degrees Celsius. Test water activity and microbial counts weekly. Shelf life remains acceptable at 4 weeks. For advanced applications, food scientists use sophisticated instrumental methods. Gas chromatography separates and identifies volatile flavor compounds. This reveals exact chemical composition of aromas. HPLC measures non-volatile compounds, vitamins, preservatives, pigments, essential for nutritional labeling and regulatory compliance. DSC measures thermal properties, melting points, crystallization behavior, glass transitions, critical for chocolate tempering and frozen food quality. NIR spectroscopy rapidly measures protein, fat, moisture, and fiber content without sample destruction, used for high throughput quality control. Proper statistical analysis transforms raw data into actionable insights. ANOVA determines if differences between samples are statistically significant. For example, testing if 3 flour types produce significantly different cookie textures. The F statistic equals mean square between groups divided by mean square within groups. High F values indicate significant differences. Regression models relationships between variables, for instance, predicting cookie hardness from baking time and temperature. Critical question: why is replication important? Single measurements can be flukes. Triplicate testing minimum provides statistical validity. More replicates increase confidence. Manufacturing uses control charts to monitor consistency over time. Control limits are typically set at 3 standard deviations from the mean. Values outside these limits indicate process problems requiring investigation. Target viscosity is 300 centipoise, standard deviation 20. Upper control limit is 360. Lower limit is 240. Daily testing plots on chart. Understanding correlations between different tests improves efficiency. Cookie hardness negatively correlates with moisture. As moisture increases 1%, hardness decreases approximately 100 grams force. This relationship enables predictive modeling. L-star values decrease linearly with baking time. Each additional minute reduces L-star by approximately 2 units. This allows visual quality control. Let me provide a practical strategy for implementing testing programs. Identify 3 to 5 most critical quality attributes. For bread, texture, moisture, color. For sauce, viscosity, pH, color. For meat, tenderness, moisture, microbial safety. Daily testing for critical safety parameters like pH in acidified foods. Weekly for quality attributes like texture. Monthly for comprehensive nutrient analysis. Based on baseline testing and consumer preferences, establish target ranges. For example, yogurt pH must be 4.2 to 4.6. Proper training ensures consistent, accurate results. Technicians must understand calibration, sampling procedures, and data recording. Maintain detailed records, test methods, equipment calibration, results, deviations, corrective actions, essential for troubleshooting and regulatory compliance. Let's discuss troubleshooting when test results indicate problems. If texture measurements vary widely, check sample preparation consistency. Ensure uniform size, temperature, and testing location on product. If pH changes during storage, investigate microbial activity or chemical reactions. Test for contamination. Verify preservative levels. Color degradation suggests oxidation, heat damage, or light exposure. Test for lipid oxidation. Verify packaging integrity. Check storage conditions. Inconsistent viscosity indicates formulation or process variability. Verify ingredient weights, mixing time and speed, and temperature control. Testing requires investment. Let's analyze when it's justified. Premium products with high profit margins warrant comprehensive testing. Artisan chocolate might justify DSC and flavor profiling. Mass-produced crackers need basic quality checks. Never compromise on safety testing regardless of cost. Pathogen testing, pH of acidified foods, water activity of shelf-stable products are non-negotiable. Identify hazards and test accordingly. Raw meat requires extensive microbial testing. Dried pasta needs mainly moisture and insect inspection. Food testing continues evolving with new technologies. Hyperspectral cameras capture hundreds of wavelengths simultaneously. This detects surface defects, contamination, and compositional variations in real time on production lines. Sensor arrays mimic human olfaction and taste. These instruments provide rapid, objective flavor profiling without trained panels. Blockchain technology tracks testing data through supply chain. Consumers can verify quality test results via smartphone. Let me summarize the key principles of food testing we've covered today. Physical tests measure texture, color, and structure. Chemical tests quantify composition. Microbiological tests ensure safety. Sensory tests confirm consumer acceptance. Test results are only valid if samples represent the batch. Use random sampling, adequate sample size, and proper handling. Regular calibration against certified standards ensures accuracy. Daily checks prevent instrument drift. Replication, proper statistical tests, and control charts transform data into reliable conclusions. Testing isn't just quality control. It's the foundation for innovation, optimization, and solving problems. Let me close with one final comprehensive example combining everything we've learned. An ice cream manufacturer receives complaints about icy texture. Let's apply our testing knowledge to solve this. Texture analysis shows large ice crystals. Average size 100 micrometers. Overrun measured at 80%. Hardness at -10 degrees Celsius is 4,000 grams force. Sugar content 15%. Fat content 10%. Total solids 38%. Freezing point -2.5 degrees Celsius. Large ice crystals suggest slow freezing or temperature fluctuations during storage. Overrun is acceptable. Sugar and fat levels are within normal ranges. Increase mix homogenization pressure to better emulsify fat. Add stabilizers to control ice crystal growth. Improve hardening tunnel freezing rate. Better cold chain management. New ice cream shows ice crystals reduced to 30 micrometers. Hardness to 2,800 grams force. Sensory panel rates smoothness at 8.2, up from 5.1. Store samples at -18 degrees Celsius for 12 weeks. Monthly testing shows ice crystal size remains stable below 40 micrometers. Success. Food testing is both science and art. It requires understanding principles, mastering techniques, and interpreting results in context. Begin with basic tests: pH, moisture, texture. As you gain experience and resources, add advanced techniques. When results seem odd, investigate. Unexpected data often reveals new insights about your product. Systematic testing transforms cooking from guesswork into precision. It enables consistent quality, innovation, and continuous improvement. This concludes our comprehensive scientific lecture on testing food properties. Apply these principles in your kitchen or laboratory to elevate your culinary science. Remember, measure, analyze, improve, repeat.